Hello there, this is Truth Socrates. Welcome to video number 27 in my series for multivariable calculus, known as Math 5C at Pasadena City College. So today we are going to do some physics, and the topic is the work done by a force field, a vector field, as it moves a particle along a curve, a path C, from one point to another. So I will see you on page 225. All right, so of course, full disclosure, I am not a physics instructor. I'm a math teacher. So the way I explain the physics in this video might not be quite the same as the way a physics instructor might teach it in their class, okay? So yeah, you might probably get something a little bit different from your physics teacher. But in any case, we are going to create a contour integral for a vector field. So we saw our vector fields last time, f, and we're going to create this integral. Okay, and check out this notation. F is a vector, and usually we have dx or dv or d whatever. But this time we have a dr, kind of like when we did contour integrals. But we have this dot product over here, okay? So that kind of makes sense because whenever we integrate something, we always want to deal with numbers, okay? Vectors are not numbers, but to make a number from two vectors, you can dot them together, okay? So that is our symbol for the contour integral of f along C, okay? So before we construct that integral, let's talk about what it means, okay? So there's basically just one interpretation for this contour integral, and that is the work done by the force as it moves a particle along C, okay? There's practically no other application of this contour integral except using this concept, okay? So let's talk about what work is supposed to mean. And yeah, in this case, it is a technical term. It has nothing to do with a job or working 9 to 5 or whatever. It is something very specific to physics. All right, so let's start with the simplest possible case. You have a constant force F, and F moves a particle from point A to point B, and the displacement vector from point A to point B, which we call D for displacement, is in the same direction as the force F, okay? So the easiest way to understand that is to drop an object. Let me get a ball. All right, so here we go. Let me move my keyboard over, okay? Anytime you drop a ball, okay, the ball goes straight down, and it falls because of its weight. Okay, so the force in this case is the weight of the ball, and the earth, of course, is pulling it downwards. We talked about gravitational field last time, and it was very universal, so to speak. We have an empty universe, and we have a planet at the origin, and everything is attracted towards that planet. This is a lot simpler, okay? Let's just pretend that the earth is flat. It's not, but objects fall straight down when you drop them, okay? So the force and the displacement are going in the same direction. Okay, so in this case, a physicist will tell you that the definition of the work is the magnitude of the force multiplied by the magnitude of the displacement vector. In plain English, this is how far the object moved. It's the distance from point A to point B. Okay, so here is a relatively simple example. So let's say that the ball is 5 kilograms. This is a lot lighter than 5 kilograms. So yeah, that's more of a bowling ball, right? Maybe even heavier. So the weight of that bowling ball is the mass times the acceleration due to gravity, 9.8 meters per second squared. If you've taken some physics, you know what I'm talking about, okay? So the weight is 49 newtons. Okay, in the English system we use pounds. You never use the English system in physics. Okay, so what are we going to do with this ball? We will drop it to the ground from a height of 3 meters. Again, keep it metric. Don't use 3 feet or 3 yards. All right, so physics tells us that the work done by gravity is the weight, 49, times the displacement, 3 meters, 147 Newton meters. That is also known by the unit of joules. Okay, so of course, Joule was a famous physicist. Okay, and again, if you've taken physics, you might recognize that as a unit of energy. Okay, so basically, this work done by gravity is the change in energy of that bowling ball. Okay, if we assume that the energy at the top is 0, by the time it falls down to the ground, it gains 147 joules of energy. Okay, that's enough to break your toes. Okay, so you definitely don't want to be under that ball when it comes crashing to the ground. Okay, so let's talk about level 2. What happens if your force is constant, but it is not pointing towards the same direction as the displacement? Okay, so it's kind of like you're pulling a cart, let's say, and the cart is moving horizontally, but you're not pulling it horizontally. Okay, you're pulling the handle of the cart at an angle. Okay, so this time physics will tell you that the only component, the only part of this force that is doing any work is the component which is in the same direction as the displacement. Okay, so that's consistent with level 1. If F were going in the same direction, you just multiply the magnitude of these two vectors. Okay, but physics says, no, if you're not going in the same direction, look for the portion which is going in the same direction. Okay, so what that means is if you have an angle of theta over here, trigonometry says you multiply the magnitude of F by the cosine of that angle, and so you will get the horizontal component in this case. Okay, so of course it doesn't matter if your displacement is going this way and your force is going this way. That angle, when you multiply F by the cosine of that angle, that gives you the amount of that force which is in the direction of the displacement. Okay, so now we multiply the two things, magnitude of F times cosine theta times the magnitude of the displacement. Oh, but wait a minute, surely you remember the alternative formula for the dot product that we saw in chapter 1. We're simply looking at the dot product of F with D in this scenario. Okay, so we are now prepared, actually, to generalize this completely. Level 3. Might as well be level infinity. Just kidding. What if your force is not constant? Okay, so in other words, as your object is moving, the force might be changing. Okay, I mean, that can happen even if you're pulling it this way. You might be getting tired, okay, or you might be getting your energy back, so now you're pulling it harder, okay? But also more generally, what if the object is not moving on a straight line, okay? What if it's moving in a circle, okay? Or, ooh, what was that? An ellipse, no? What was that? A helix, let's say, okay? So this can be happening in space. Okay, so you can be moving along a helix like that, and as you're moving, the force is changing magnitude, is changing direction. Okay, so it's going to be a completely general scenario. All right, so here's how we're going to generalize it. We have a vector function representing our force, and you have 3 components. Okay, it can be happening in space. And we have a smooth space curve parametrized by r of t. The domain of t is from a to b. Okay. Again, our integrals have to have a finite domain. Okay. So we are going to start off the process using the same idea that we did for the contour integral of a scalar function. We are going to divide our domain a to b into n subintervals of width delta t, equal widths. Okay, this sounds familiar, right? So you take b minus a, divide by n, you get a partition, and between any two successive points in this partition, you get the same width of delta t. Okay, so I thought let's refresh our memory by going back to that section, because we did talk about something different last time. We talked about vector functions. So I will see you at page 213. Okay, I'm actually at page 212 because just to show you, I literally cut and pasted what we have here in that section we were at just now. Okay, because the next step is to pick a point ti star between within each subinterval, and then we get a representative point corresponding to ti star, which is on the subarc corresponding to this subinterval. Okay, so what is important, of course, is the picture that we see on the next page. Ooh, I still fit. Okay, so what we need is this. All right, we have a different function, so ignore this. Okay, we have this space curve. Okay, and we are going to look at the subarc of that curve. Okay, so this is what we did last time. Okay, so this time we are moving a particle along the curve, and there's a force which is acting on that particle during this small period of time. Okay, so we want to know what is the work being done by that force. Okay, so now that we see that picture, let's go back to page 225 or 6, and we'll continue where we left off. Page 227, here we go. All right, so here is your subarc. The starting point is at r of ti minus 1. The ending point is at r of ti. Okay, so the displacement, of course, is given by the difference between this vector and this vector. We've done it before. So we subtract r at ti minus 1 from r of ti. So that is our displacement. Okay, and then we have a representative point, r of ti star. So the force that the particle is experiencing along this subarc, we can assume that to be almost constant, okay, because it's here for a very, very small period of time. Okay, so that force will be constant, and we will use the representative point to compute that force. Okay, so we will take the dot product then of the force with this displacement. Okay, but wait a minute, here's the displacement, and remember the trick we did last time. We multiplied and divided by delta t. Okay, and that's a smart thing to do because this difference quotient is approximately your tangent vector. Ooh, okay, so if you draw the tangent vector any point along this very, very small arc, all of those tangent vectors should look almost the same. Okay, so that tangent vector, that difference quotient, is approximately the tangent vector at ti star. Okay, so we therefore take the dot product of this force with this displacement vector. Okay, and that is the work done by the force as you move along this very, very small subarc. So as usual, to find the total force, we're going to form the Riemann sum of that dot product that we just found, and we'll take the limit as the number of intervals goes to infinity. Okay, that instantly turns into your definite integral. Okay, what are we integrating? We're integrating the force evaluated at the curve, dotted with the derivative of the parametrization of the curve. We're integrating that dt. Okay, now at the beginning of the video, you saw the symbol f dot dr. Okay, so where does dr come from? Obviously, it comes from this. Okay, so we will think of r prime, which is dr by dt, and we are going to isolate dr, sounds familiar, by multiplying across dt. Okay, so solving for dr, it looks like it's r prime of t dt. Okay, that is of course very, very crude notation, I should say. Okay, we're not literally multiplying by dt. Okay, we're defining dr by the symbol, by the formula. Take the derivative of r, multiply by dt. Okay, so that is the meaning of the dr in our symbol for the contour integral. Okay, so that is what we are going to use to define the work done by a continuous force field F, specified by this. As it moves a particle along a smooth space curve C, we have a parametrization for C, and a domain for C. It is the contour integral along C of F dot dr, which means integrate from A to B, the force field evaluated at the curve r of t, plug in the parametrization, find the dot product, find the derivative rather, r prime of t, take the dot product, that is what you integrate. So click, this is our algorithm. Okay, so step one, if you don't have a parametrization, make one. Okay, if you're given a curve that you're supposed to know how to parameterize, then they expect you to be able to parameterize it on your own. Now that you have that parametrization, plug in x of t wherever you see x, plug in y of t wherever you see y, and so on. Okay? Next, find the derivative r prime of t. Okay? Check that your curve is smooth. Okay? If it's not smooth at one point, we'll forgive that. Okay? Maybe we'll stop at that point and then continue. Okay, take the dot product of the results from these two steps, simplify if you can, and that is what you are going to integrate from A to B. Okay, so yeah, I would strongly suggest that you do the plug-in first before you take the derivative, because one of the biggest mistakes that you can make, I've seen it so many times, you plug in the components of r prime into p, q, and r. Okay, no. You plug in the original parameters, these expressions, into your x, y, and z. Okay, so let's go to our workroom and we will solve an example. All right, how appropriate. We're going to find the work done by this force in our workroom. So we have this force over here. We want to move a particle from this point to this point. Find the work done. Okay, so what are the steps? Step one, do we have a parametrization? No, this is empty. We're supposed to find it ourselves. Okay, so yeah, remember what to do, do you? We need a displacement vector. Okay, so 3 minus 1 will need 4. 1 minus 2 will need -1. -2 minus 0, -2. Okay, so that's our displacement vector. We start here and we finish here. Okay, so we'll go -1 plus 4t. And then we have 2 minus t. And then finally we have 0 minus 2t. Okay, so of course we can just write that as minus 2t. You remember the domain? T goes from 0 to 1. Okay, so quick check. When t is 0, these go away and you're left with -1, 2, 0. That's where we start. When t is 1, what do we get? 4 minus 1, 3. 2 minus 1, 1. -2 times 1, -2. Okay, so we end at that terminal point. All right, so now we plug in that parametrization into f. Okay, so it is literally a find and replace. Okay, so I call that f evaluated at r of t. Okay, how many x's we have? Oh, I got a message. We have 2 x's over here. So replace x with that and that. Okay. We got 2 y's. Y is over here. So we multiply 4 times this. Remember to put parentheses. Keep using page down. Now you see what we're going to do next. There's our other y, and now finally our z. Okay, minus 2z, so minus 2 times this, and this, and, oh, almost missed one. There we go. Okay, so, yeah, there's some algebra involved. Okay, so we have to expand this, multiply this, simplify that, and then do the same here. We have to multiply that, expand that, and expand, expand, simplify. Okay. So, who are you? Compute and simplify. Okay, there we go. That's better. So that's the third component. Yeah, so let's make our final answer. And let's see. Okay, let me use this one. So it has fewer stuff we have to erase. Boom, and boom, and boom. Okay, so this is our z component. I always like doing it from the end. Okay, and then who is our y? Our y is over here. So compute, simplify. Yeah, okay, there we go. That is our y over here. And who is our x? I'll try to do that myself. 4t plus 12t is 18t and minus 3. Okay, do I dare check if I am correct? Compute and simplify. 16. Oh, I knew I would make a mistake. What did I say? 4 and 12 is 18. Ugh, how embarrassing. 16t minus 3. Okay, so that is our force field. And the next step is r prime of t. What is r prime of t? It is, okay, take the derivative of every component. First one is just 4. Okay, second one is -1. And third one is -2. Ooh, where have I seen that before? 4 minus 1. It's right there. Yeah? Of course, the direction vector is the derivative of your parametrization. We saw that at the beginning of the chapter. Okay, so now we take the dot product. Okay, so we take 4 minus 1 and minus 2. We are going to multiply with the corresponding component in our f. Here, minus 1 times this, so we're just basically subtracting that. And then minus 2 times this. Oh goody, more algebra. Okay, so yeah, it's a good thing. Yeah, it's just a quadratic, okay? So, compute, simplify, and yep, okay, so that's what we get. All right, so now we're ready to find the work. Turn to the left. Oh, what's our domain? 0 to 1. Integral from 0 to 1 of minus 22t squared plus 100t minus 5 dt. Okay, so of course, we all know how to do that. Minus 22 over 3t cubed plus 52 squared minus 5t. So we go from 0 to 1. Ooh, I can almost do that in my head. Remember how that worked last time. minus 22 over 3 times 1 plus 50 times 1, 50t squared, yes, becomes 1 times 50 minus 5t minus 5. Okay, so compute that fraction, simplify, and that, okay, any chance I'm correct this time? And oh, I got one, yay. All right, so there's one more thing we have to learn for this, and so we're going to go back to our PDF. We're not going to GeoGebra today. Woohoo! Okay, so we're going to make one more kind of integral, actually 3 kinds, 3 flavors. But to do that, we are going to literally expand that single integral that we saw using the 3 components. Okay, so what were the steps? Start with the parametrization, and then you plug this into your function. Okay, so x becomes xt, 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 and so on, yt's and zt's. Next, we go back to the parametrization. You find the derivatives of the components. After that, we take the dot product. So you multiply this p with x prime, this q with y prime, this r with z prime. Okay, so there it is. That big mess is what we integrate from a to b. Okay, however, we can split it up into 3 terms, 3 integrals. Okay, so we have this dt, and this dt. Okay, so you might think, big deal. Okay, what's so special about that? Well, remember how we said that let's call r prime of t dt dr. Okay, so in the same way, let's call x prime of t dt just dx, y prime of t dt dy, z prime of t dt, call it dz. Okay, so if we don't write x, y, and z within our p, q, and r, we're looking at the contour integral along c of a pdx, okay, plus a contour integral along c of a q dy, plus a contour integral along c of r dz. Okay, so you can think of this as the contributions of p, q, and r to the total work. Okay, so if you actually split up your force, instead of a single person pushing or pulling your object, you have 3 people. One of them pulling only along the x, one of them pulling only along the y, and one of them pulling only along the z, pulling upwards. Okay, those 3 people are sharing the work, the total work done by F to move your particle from one point to another. Okay, so for our final example, we're going to compute one of these 3 integrals. Okay, so here is our second example. We want to find the contour integral along c of 5x minus 2y plus 3z squared dz. Okay, not dx, not dy, just dz. Okay, and c is the elliptic helix parametrized by 3 cosine t, 2t, 5 sine t, and we're only going to do a quarter period from 0 to pi over 2. Okay, speaking of period, there we go. Now it's a sentence. Okay, so if you recall when we did contour integrals with respect to arc length, we had a magnitude, okay, magnitude of r prime of t, and yeah, I didn't point out, that didn't show up for this contour integral, okay, which means that we don't have a pesky square root to deal with unless it's somewhere in the function. Oh good, I don't see any functions and any square roots over there. Okay, so this means that we have a lot more flexibility as to the kind of curves that we can integrate on in this section, as opposed to the first time we saw contour integration. Okay, enough talking. what are we going to do first? Plug in the parameterization into our function. Okay, so notice we don't have a vector function. We only have a function, a scalar function in x, y, and z. Okay, so because that's z, dz, this is like your r of x, y, z. Okay, so we want to plug in x in there. So replace x by free cosine, y by 2t, z by 5 sine t. Okay, there you go. So yeah, that's not too bad. That's 15 cosine of t minus 4t plus 5 squared. 25 times 3, 75 sine squared of t. Okay, so that, there's more. There's more. We still have to find our dz. Okay, so remember that dz means z prime of t dt. Okay, but wait a minute. Who is z? It's this one. Okay, z of t is 5 sine of t. Okay, so if you see that you're integrating dz, you have to look at your z component for r, and you need the derivative. Okay, so z prime of t equals 5 cosine of t dt. Okay. All right. So, yeah, this, I should move that over there. Okay. So now our integrand is going to be the product of what we did in step 1, since we already have the parametrization there. And we will multiply, whoops, fine. There we go. We will multiply by our z prime, 5 cosine of t dt. Okay, 5 cosine t and dt. Okay, so of course that's the dt that goes into our integral. Okay, now, remember we are going to integrate this. We have the unpleasant task of integrating this. So, well, first of all, that will be our setup, integral from 0 to pi over 2 of that thing. Okay. So, well, obviously we can take the 5 out. Anything else we can take out? Nope. That's it. So 5 of that, and take away that 5, and we don't need that parenthesis anymore. Okay. So now, to integrate this, we'll need to distribute cosine first. Okay, so that will be cosine squared over there. And then 4t cosine of t. Oh no, how do we integrate that? And then 75 sine squared of t cosine t. Okay, so we have distributed the cosine of t. Okay. We have 3 things that we need to integrate. I'm pretty sure you know how to do cosine squared because we've done that a gazillion times, right? So we convert to 1 plus cosine of 2t divided by 2. Okay. What about this one? Okay. Do you know what to do? If you were sitting right there in front of me, I would be asking, what integration technique should you be thinking of? Do you know what to do? We integrate by parts, okay? So we have u equals t, and we have dv is cosine of t, okay? So du is t, and our v is integral of, oops, I forgot the dt. The integral is sine of t. Okay, so the antiderivative that we want for t cosine t dt is uv, so t times sine t minus integral of v du, so that is sine of t dt. And of course, we know how to integrate sine of t, that is negative cosine. So in the end, we're going to get plus cosine. Forget the plus c. Okay, quick check. What's the derivative? Product rule, t times cosine of t, which is our integrand, plus sine of t times 1, and then cosine becomes negative sine. Okay, so that is the correct antiderivative. But why should you believe me? I make mistakes all the time. So cosine t plus t sine of t, correct. I don't know why. Scientific notebook does not put parentheses around the argument for trig functions. I don't get it. See, we have to write the t's ourselves. Okay, so that takes care of the second one. What about the third? Do we know how to integrate sine squared of t cosine t dt? Should we do integration by parts? I do believe there is a simpler way to do it, right? Do you see what I see? Do you see what I see? Just a simple u substitution. Okay, so if you let u be sine of t, then our du is cosine of t dt. Much simpler, right? So we're basically integrating u squared du. So this is 1/3 of, oops, I need an equals, 1/3 of sine cubed of t. Okay, all right, so we know how to find this. Been there, done that, hated it. So we know how to do all of those. And of course, we plug in 0 to pi over 2 in our antiderivative. You know what to do. So let's just skip to our final answer. That will be our final answer. Okay, so no surprise. Part of it is in pi. Part of it is just an integer in this case. But usually, you'll get a rational number, some fraction. Okay. That was our work for today. No pun intended. Of course, pun totally intended. So I hope you enjoyed that video. Maybe you will remember me when you take your physics class and you find the work done by an electric field or a magnetic field. So that's our video for today. I hope you enjoy the rest of your day, and I will see you at our next video. Bye.